All right, well, it's time for another Physics Teachers Are Awesome reaction. It's been a long time since I did it, but I thought, you know what, let's get this going again. So what we have here is, I think this is a college lecture. My guess is thermal versus classical, lecture 3.1. So we're a little ways into the term, and I think he might be writing on a glass thing, so if it looks like he's left-handed, he's probably really right-handed, so see how it goes. Here we are.
In the last lecture, we discussed classical thermodynamics, which we said is a control theory, which is distinct from a dynamical theory, and which deals with isolated systems, which the user, who is an integral part of this kind of theory, puts together and allows to interact in various ways.
Cool.
We said that an integral part of that was simple systems, these isolated objects, atomic inside of the theory, which have no internal degrees of freedom, but only parameters that describe their totality.
Cool.
In this lecture, we're going to get a little deeper on that concept and start thinking about what a simple system means both in the theory and how it corresponds to objects that we might encounter out there in the world. So I'm going to start us off with an analogy to classical mechanics. Recall that in the last lecture we talked about the state space of classical mechanics. Let's talk about.
Okay, so definitely writing on a glass board. So I did one of these, I don't know, a year ago or something, where I really got freaked out because someone was using the right-hand rule. And they were using what looked like their left hand. It was super confusing. I would guess that in this lecture, it's not going to matter. And I really, really love it. There's obviously the black background, and we're going to be able to read it clearly, and he's going to be able to keep looking at us. So I've really, really liked this way of doing it. I wonder if this is a studio that he set up or if his school sets up for him. Not sure.
About state space for a given particle. Well, that state space is going to be the space of possible positions and momenta that has. Let's say that it's, for instance, in this case, R3 cross R3, where the first R3 is the space of positions and the second R3 is the space of momenta.
So right away you can tell that there's some pre-work that people have been doing in this class. This is probably not something you would do in a high school class. But what's happening here is the very first thing I thought of when I saw this cross product, I thought of cross product. I was like, is that actually a good way to think about it? And what's cool about cross products is you get two vectors, you can cross them, and boom, you get the third dimension. So I actually think that cross products is a good way of thinking about sort of multiplying dimensions here. So what he's saying, of course, is that it can have 3 degrees of freedom in its position and 3 degrees of freedom in its momentum. What's interesting is you think of these as being positional. You don't immediately think of this as being how you think of momentum, like should there be a capital P here or something. But I like the fact that he's talking about how many different possibilities there are, because that's the problem with thermo, right? Is there's just too much crap going on, and so it'll be really interesting to see where he's going. You can see he's going to get to energy and work. I don't know if I'll keep the video going that long, but I'm really curious to see how he establishes this, because I think this stuff is really fascinating.
Now, there's one other thing that we need in order to or I should say, two other things that we need in order to say more about this theory. We need its initial condition, just as we said yesterday. And we need a rule that tells us how it evolves forward in time.
Ooh, I like that.
In particular, that rule was Newton's second law.
Okay, I love where this is going. Ooh, wow, look at that.
Now, the key thing to realize here.
So think about, what they must have done in the previous class, right? They're saying, okay, where you are, how fast you're going, and then can that predict where you're going to be in the next little bit of time? Well, if there's no force, really that's all you need, right? Where am I going? How fast am I going? Okay, I can tell you where I'm going to be. And clearly last time they were talking about the forces here. I find it fascinating that he doesn't have the momentum in here. So let's say you had a frictional drag force or something. But perhaps by this he means it's also its derivatives. It's not 100% clear. So the other thing, of course, is that what's fascinating is the connection between these initial conditions and this number 2 here, right? So you're going to need to be able to provide these and these before you can get this going. And of course, even though I try really hard to do it myself, This is really a hard way to do it for, Avogadro's number of atoms. So I'm really excited to see how this analogy is going to work, because there's going to be some initial condition, I don't know, maybe pressure or something like that. And then I'm really curious to see how he talks about the rule here.
Is that F has a special role in this theory.
I really love how the board works. I wonder if yellow would work better, though.
We say it governs.
I think white's working pretty well. On his cheek, the white is struggling.
In the sense that F encodes all of the information that we
Different
need
color.
in order to say what this rule is that tells us.
Wow, that pink is so cool. It looked like he was highlighting. Okay, so I like what he's doing here. He's talking about the force being the governing body. And so I'm just trying to think ahead to the way he's going to talk about this with the thermodynamics. What governs? Oh man, it's so cool.
Us about the dynamics. F isn't the rule itself, but it does include the information we need to get the rule.
Love it.
Now, let's try and analogize that to classical thermodynamics.
Another color
Now,
looks like
I have a
maybe.
little bit of experience with it. In this case, our state space,
No, that's still
as we
white.
said in the last lecture, is something like gamma 1 times gamma 2 times ... times gamma k, where each gamma is the state space for one of these simple systems that constitutes the whole system. Or I should say it's a constituent piece of the whole system. We also need an initial condition. And we said that our rule was composed of the possible different operations, or I should say, the analogy of a rule that we get in this case.
Oh. Takes a while to erase.
Is a list of allowable operations.
That's so interesting. Because it's so clean when he started. Oh, look, the erasing is getting better and better as time goes
The
on.
allowable operations all make entropy either go up or stay the same. X increases,
Interesting.
stays the same.
So, again, I don't know sort of where this sits. The fact that there's this number 3 tells me that this is maybe the third section they're covering. So, I don't know, maybe this is week 3, or I don't think this is day number 3. But to already be talking about entropy increasing or stays the same also tells me that this might not be an introductory lecture, which also I think that this vocabulary basically tells me this is maybe for upper division. I don't know, maybe it's even a graduate class. But to jump right away into entropy tells me that these 2 points are going to be really, really interesting.
And we talked a little bit about what those operations were in the last lecture. We'll get a little deeper into what they are in the next lecture.
I also wanted to comment on something. I actually think there's something interesting about the focusing of the camera. I don't know about you, but this looks more clear than this does. It's essentially the same exact phrase. It's the same handwriting. And so could it be that this is because of the erasing? Or could it be that this camera doesn't have a full focal plane, and maybe the focal plane is bent, which of course most cameras has to have a little bit of distortion towards the edges. But over here this looks really, really great. But I don't know, maybe it's just my eyes, but everything over here is just slightly out of focus, even while this stays in focus. And of course, he looks pretty in focus as well. I'm looking here right at the edges here, so, and he's got to be, a rough arm's length away from the glass or plastic. So I'm not 100% sure why this is a little bit blurry. I mean, obviously still readable, so who cares? But I don't know, I find that really interesting. It also could be YouTube. Is it possible that's YouTube doing that? I'm not sure. Put your thoughts in the comments.
But the point is that S has the same kind of special role as F does for a classical theory.
Wow. Same kind of special role.
S governs the dynamics. Not the dynamics, but rather the control operations. Because we don't have
that's subtle.
dynamics.
So, I wonder how far you can push that analogy. Could you say a force pushes something, entropy pushes something, a force pulls something, entropy pulls something? he's talking about a subtle analogy about what governs the behavior, and he said governs the controlling. He corrected himself, but I guess I didn't catch exactly what he corrected. Wow, super interesting.
So this analogy should help us make sense of what's going on. In classical mechanics, this is what we would have for one particle. But what would we have for capital N particles? Well, each of these would just be raised to the n. And now we would have a sum over all of the particles.
Here's where the white is not working super great, but we can see it, and he'll get out of the way. Yep. It's so interesting to watch him thinking, right? And so that's actually a really subtle thing that students wouldn't normally see when you're writing on, let's say, a blackboard or a whiteboard, and your back is showing to them. So let's watch that again. Let me just go back just a little bit forward. As soon as right there. That look. Because what I was wondering is he talking about summing all of the forces and figuring out that, assuming all the forces apply to all the particles? That's what I was thinking, right? And so I was thinking, boy, is he going to actually put an equal sign here and put a sum on the forces, or is he going to put parentheses here, or is he going to stop? But you see this look on his face, right? It's fascinating. I love that he's thinking it through, right? Because he really wants to drive this analogy home. And this look on his face is something that normally the students don't see or even pick up on. All they see is just the back of his back and think, okay, well, maybe he'll get out of the way. Eventually I can see what he's writing, which is the beauty, of course, of this setup. But I also wonder if this setup gives him the pause ability. Like, could he actually pause the camera and say, and erase? Or we've only seen him make one small correction. It was what he did up here. So I really love this thinking, and it looks like he comes out of it with a choice. But let's see how it is.
Oh, I'm sorry. No sum. But we would have a rule that the jth particle obeys. Which might, in principle, depend on the positions of all of the particles.
Yeah. Oof, yeah, exactly. And maybe the speed of the one. But, without doing frictional form. Yeah, okay. There we go. Fascinating. So you saw what happened. He was like, I don't like what I'm doing here. I need to think about this. I think what he did to make the correction was great. He's like, actually, and then he sort of erased the sum and kept moving. Now, I talk a lot, or I should say I think a lot about how to best do that for students, right? Like, if they're writing along with you, is it just as easy for them to erase, or should you rewrite because they're going to rewrite? But I think in this case, with video and the beauty of being able to fast forward, rewind, all of that stuff, who cares about that, right? This should just be a good, solid presentation. I don't know if he has the ability to pause the video easily. He could have done that and just redone. But I think that this was certainly a small enough, adjustment that it was fine to do on the fly. I actually think he did a really great job of it.
So now the whole set F sub j governs the dynamics.
Yeah, and will entropy do that? I don't think entropy will do that.
We have something like a set of n different state spaces which come together to form the whole state space. And an F which tells us how those sort of particles interact. In the same way, S is going to tell us about how these different state spaces, which we number 1 through k, interact in classical thermodynamics. Now I'm going to clean up the board, and then we'll get a little bit into what these simple systems would look like, both in real life and in our model.
So I was wondering if this would happen. So clearly he does have the ability to pause the video. So let's go back and see, was he reaching for something?
These would look like, both in real life and in our model. Okay.
Yeah, I think there's something down below
Let's
he could
get to
touch.
what a
Interesting.
simple system is and sort of what are state spaces for simple systems do.
So it makes me think about, right, like, so if he has that ability, he could prep the board with some stuff. So he clearly did prep his board with kind of the outline. But what he's doing now, he feels comfortable, and I think it's working really great to sort of talk and write at the same time.
Now, in
Ooh,
this
that was
context,
cool.
I'm going to deal with these.
I really like reminding people that, hey, I really am following an outline. That was actually really cool, just that little checkbox.
Simple system as a model. We're not going to talk about how we would spot one in the wild until we sort of have laid the model out itself. So we said that a simple system has a state space gamma. And this state space is some kind of subset of R, let's say M. Fair enough. That means that it can be described by M parameters. But with that being said, we need to figure out what those M parameters are. And to do that, we need to talk about thermodynamic variables and the kinds of variables that we'll encounter in thermodynamics.
Now that looks nicely in focus. I mean, that looks perfectly in focus.
Okay, thermodynamic variables have at least two features. The first is that each one has a magnitude.
Now, you know that normal physics students who maybe gone through an introductory level or high school would say, and of course a direction. My guess is he's not going to talk about a direction for thermodynamic variables.
And the second is that each has a type.
Aha.
Now, I'm going to use the term type here rather than unit, which typically would be used in this context.
Aha.
And all that I mean by this is that two quantities which have the same type might have different units. Type here being something like length, mass, time, anything of that type. So, for instance, 1 inch and 1 kilometer both have type length.
Cool.
And in this context also both have magnitude 1. All right, so in any case, these are the features, but in fact there's more. Some thermodynamic variables have a third property called extensivity or intensity.
Whoa.
Extensivity.
Oh. Yeah, it's just like erasing with the finger on the whiteboard. You get grease on there, and then that part's not going to erase that well later.
Now, it's important to note that within the model, there is no way that you can tell whether a variable will be extensive or intensive. There's nothing that you can tell that you use to derive the extensivity or intensity within the model. It's just something that you need to know. But when we make these correspondences to the real world that we actually live in, it's important that we know when something is extensive or intensive. An extensive quantity is one for which if we take our system and we make m copies of it, then that quantity will increase by a factor of m. An intensive quantity is one such that if we do the same operation, this quantity will not increase at all. So for example, if we have an object that has volume, let's say for instance 1 cubic meter, and we make 10 copies of that object, and we shove them together, the resulting mega object will have precisely 10 cubic meters of volume. However, if that original object was at 200 Kelvin, and we make 10 copies of the object and shove them together, the resulting object will still be 200 Kelvin.
Yeah, that's really subtle.
Sort of just diagrammatic.
You know, it's been a long time since I've taught this at this level, so what I'm trying to think about, it was the statement that he made about it's impossible to know when you first sort of encounter something, whether it's impossible to kind of like derive whether something extensive or intensive. And so as I think about this, I think about kind of like the definition of it. And so if you think about temperature as being related to like the average energy of something, because you use the word average, it wouldn't matter how many things there are. So it would seem like that fundamental definition of temperature would allow you to know that that's I think that's what he described, an intense intensivity, an intensive object. So that would be really, really interesting to think about, because it's so subtle, right? To know, can you know what the heck you're up to, or do you sort of have to look to see what its effects are? So this is getting a little long, so I think I'm going to stop here, but I just really loved how he was setting this stuff up. I think that, if you think about the difference between the classical stuff, the force stuff, and the particles, all of these things, length, time, mass, they're just so straightforward compared to the things that you have to do in thermodynamics, right? Even what he was just saying, who would have ever thought that sometimes it adds and sometimes it doesn't? That's why this is so hard. And I just want to say a few things about what I really liked about this. Obviously, I like the setup. I think that the whiteboard is super awesome. I think it's very cool how he really has this down. And as far as I can tell, it's not looking for add notes at all. I loved how he adjusted to and sort of gave that pause where he was staring at that one equation he had with the sum. I thought that was really, really interesting how he did that. And I just love this constant connection to what students already know, so this analogy. So I thought this was really, really great. All right, everybody, have a great day. And remember, physics teachers are awesome.